All right, chapter 5.3 is going to be your favorite chapter. It has for us the fundamental theorem of integral calculus, which, if you recall the problems we just did last chapter with this integral symbol here, and we had to graph it, or we had to use this midpoint formula with 20 rectangles to get the answers. The reason I like to do it those ways first is because sometimes these are hard to do this way because you can't figure out the antiderivative. You have to find the antiderivative. Big F is the antiderivative of little f. All right? If you can find the antiderivative, it's real simple. If you can't find the antiderivative, then falling back to a midpoint method to get an approximate answer, or maybe a geometric method to find the exact answer using geometry, would be necessary. Basically, all this is saying is to evaluate this expression here, which is the type of expressions we saw in chapter 5.2, you find the antiderivative of f of x, and you do the antiderivative evaluated at the end of the interval, a big number, minus the antiderivative evaluated at the beginning of the interval. The only requirement is that the function f of x is continuous on every value from a to b, including a and b, meaning there are no undefined values on the interval. Let me give you an example, one that wouldn't work. If I had 7 over x from negative 2 to 2, 7 over x from negative 2 to 2, 0 is within that interval. 7 divided by 0 is undefined. That does not exist because there's division by 0. All right, so you can't do it. That hasn't, I mean, even if you tried the midpoint method, the answer you got would be invalid. It wouldn't be correct. All right, we haven't seen one like that yet because we haven't dealt with this theorem yet, but just know that the first step of every one of these problems when you look at these is this function undefined for any value on this interval? If it is, you're done. It does not exist because it's undefined. All right, and that will happen in at least one of the problems today. So let's take a look at example 1. Evaluate from negative 3 to 1 x squared dx, or explain why it does not exist. All right, so, and I'm going to give this nice little disclaimer each time right now, and even on the test I think I do that, because sometimes it doesn't exist, and it's nice to have a little reminder that, oh yeah, I'm supposed to check that first. So, if I'm trying to take x squared, is there any value between negative 3 and 1 where x squared is undefined? No. So we have to do it. All right. What's the antiderivative of x squared? X cubed divided by 3, and then plus c, right? Yep. We're using good antiderivative technique. We're going to put a constant there because there might be some constant involved. All right. Now, just a nice little note here on notation. Once I've written the antiderivative, the way you write the operation that we're about to do, the way your work is supposed to look on your paper is this. You put a bracket and you put the small number to the big number over here. Once you've actually established what the antiderivative is, you put that little notation there on your paper. All that means is that I want to evaluate this function at this number and subtract this function at this number. So if I do that, if I substitute x with the number 1, I'm going to get 1 cubed over 3 plus c minus, and then if I substitute negative 3 in, I'm going to get negative 3 cubed over 3 plus c. Now you might be thinking to yourself right now that plus c is going to get in the way because I don't know what c equals. All right? But let's just see what happens to that as we go through this. 1 to the third is 1. So 1/3 plus c. And then negative 3 to the third is negative 27. Negative 27 over 3 is negative 9. If I distribute that minus sign through, I end up with 1/3 plus c plus 9 minus c. What happens to the c's?
Cancel.
They cancel. That's going to happen every single time. If you're using the fundamental theorem of integral calculus, the c's always cancel. Reason why is because it's always going to be plus c here, it's always going to be plus c here, it's always being subtracted, so you always distribute that minus sign through. So honestly, when I'm doing definite integrals with the fundamental theorem of calculus, I actually don't put the plus c in my work usually. I put it there just to show you why, but for future problems I'm not going to be doing that. All right? And then what's left to do is to add these up. That's 27/3, right? So I maybe not reducing the fraction would have been a better plan, but 27/3 plus 1/3 makes 28/3. And that's the answer. All right, that's the exact answer to that problem, down to the millionth decimal place. All right, and it works, again, as long as it's defined on the interval, that technique always works. Gets you the right answer without too much fuss.